everybody's having a great Tuesday. Some of us actually, I saw a couple people on the line from Australia, so hopefully you're having a good early Wednesday morning. But everybody's in for a good one today. We're getting 6 and 60. That is 6 load handling lessons in 60 minutes. Well, give or take. Should be 60 minutes-ish. So our guest host today is Jonathan Parnell. Jonathan's a project manager here at ITI. So let's jump right in and get started. So very briefly, just a little bit of background information on ITI. We strive to be the world leader in education and technical services for organizations that utilize cranes, rigging, and load handling equipment. So we've been fortunate enough to work with some amazing companies, as you can see on the screen there, and many more that aren't visible. ITI currently has 3 training centers in North America, and we have trainers based in the US, Canada, and Brazil. And speaking of our technical team, here they are. These are our all-stars here. As I mentioned, we have trainers and consultants from all over the world, and they're based primarily in the US, Canada, and Brazil. I wish I could probably spend an hour talking about each one of these guys and their accomplishments in the industry and everything they got to get to this point, but unfortunately I can't do that. So if you want to read up on our trainers and consultants, please visit iti.com/staff. So as I mentioned before, Jonathan Parnell is your host today. Jonathan is our in-house engineer here at ITI, and he joined us via the U.S. Military Academy and then later Missouri University of Science and Technology. So after his time at West Point, Jonathan actually served on active duty for 5 years, and that included a tour of duty in Iraq. Here at ITI, Jonathan, he's worked on a number of field service projects, including accident investigations, crane and rigging audits, or performance evaluations, as we often call them, and then critical lift plan development and review. I don't want to waste much more of our time because I'm really excited to get to the meat of our presentation today. I do want to remind everyone, if you have questions during the presentation, please enter them into the question pane on your dashboard there. I'll be collecting them. I'm not going to interrupt Jonathan as we're going along, but I'll be collecting them and hopefully get them to him at the end during the Q&A session. So I'm going to pass the screen over to Jonathan. We have some pretty cool poll questions too, so look out for those. We really want to get you guys involved and hope everybody finds this valuable. So Jonathan, go ahead and take it away.
Jonah, thanks for the introduction. This is Jonathan Parnell. I'm really excited to be here and presenting. As an engineer, you can imagine they don't let us out much, but when they do, we try to do our best. Today, I wanted to talk to you about some learning objectives, and really, it's kind of a showcase of knowledge centers that we present corporately. And the topics we're going to talk about today include rigging gear inspection, advanced rigging, critical lift, planning, mobile crane inspection, mobile crane operation, and rigging engineering. And we're just going to take little snippets from each one of those learning centers and just kind of boil it down to one objective, jump into it, kind of learn something about it, then move right on. Again, if you have questions about anything that we teach today or anything in general in terms of rigging or crane operation, don't hesitate to ask. I'll be happy to answer any questions after the webinar and even via email or phone call. So let's jump right into it. Some of the training subjects, just for everyone's knowledge and edification, in our rigging and gear inspection course, we talk a lot about really the big hardware pieces when it comes to rigging and cranes, and those include wire rope slings, kind of what we're trying to look for in terms of damage or what can remove that piece of equipment from service. Then we move into synthetic slings, chain slings, rigging hardware, shackles and sheaves and blocks and all the pieces of hardware that we use on a daily basis. So there's just some of the training subjects, and they're all kind of grouped around the criteria based in our federal regulations, OSHA, and ASME standards. So as we look into the rigging gear inspection section, we'll look at the first learning objective, and we're going to talk about how to or be able to recognize and identify field damaged rigging samples, and really based on the guidelines we've established in the industry itself. What constitutes damage, and what is going to keep us safe by removing that equipment from service, get it serviced or get it discarded, so that we're staying within the working limits of those pieces of hardware. So one of the pieces of documentation you may have received, if you got a chance to open up your PDF document at all, was a document we call the rigging gear inspection card. And really this is just a full card of information and when it comes to inspecting and evaluating pieces of equipment in your inventory. And you can see here that if we look specifically at web slings, synthetic web slings, we see a lot of different information based on what we come about from OSHA CFR 1910, as well as ASME standards, both of those, and those are actually all three of them are color-coded on the card itself for better identification of where that information originated. And so finally, we've got good practices, just kind of the best things that we found throughout the industry and our own experience for how to protect these web slings for their long-term use. And so we're going to use some of this criteria to evaluate some of the slings. I just want to kind of show you this and let you see and evaluate for yourself. And if you guys have any additional good best practices that you guys use, I'd love to hear about them. So moving back into our presentation here, we can see that some of the information were things like damaged or cut webbing, the body of the web itself. We can see that, pardon my ink here. Let me jump into this one more time and see if we can get this going. But one of the things you can see is cuts, abrasion. What else was there? There was, we could see, yeah, cuts, holes, cuts, or snags and crushing. Missing or legible tags, that's really from the manufacturer, and they should be the ones that tag those. And that's going to identify who made it, possibly when they made it, what its capacity is. And those are really useful information pieces for the user at the end of the line. One of the big things about synthetic web slings is they're really susceptible to UV and sunlight damage, and we've seen studies over and over again about how much damage they can receive from just being out in the sunlight. And some of the southern states have big problems with this, so they keep most of their equipment stored indoors and out of that sunlight. And I think they're good, but even UV damage from indoor lighting can cause problems. Moving into this category again, we're kind of looking at, it doesn't only include the web sling itself. If you look down further, you notice kind of the comments down here, bent hook and spread. The hook is spread more than 5% or a quarter inch, and really that has to do with the end fittings, and I'm referencing B30.9 here. The end fittings also count as part of the synthetic sling, and so even if the web sling is perfectly fine, there's no cuts, no damage to what you can see, the end fitting still matters. It's sort of the the weakest link, so to speak. And so when we kind of look at this, we're looking for end fitting damage. Kind of moving on, we'll talk about the tag as well, right? So we talked about missing or illegible. And much of what we see in synthetic web sling removal criteria can also be said for chain sling removal criteria. And let's look at the next slide down here. Panel 3 of our rigging gear inspection card also talks about alloy chain slings. We get a lot of our information here from ASME B30.9 as well as point 10 because that deals with the end fittings as well. We use chain slings a lot of times for heavy-duty knuckle dragon type work, and what this really means is we tend to put it in environments that are caustic and abrasive and expected to do really well, and they tend to, but we still need to be aware that maybe those hot environments or even cold environments can really play a major role in reducing the capacity of our rigging gear. And so we'll look for things like, such as, again, manufacturing tag, check the chain for and attachments for wear, nicks, cracks, all those things that would kind of lend itself to being removed from service, potentially repaired and then put back into service once we've deemed they're acceptable. Discoloration or from excessive temperature, weld splatter, stretching of any kind, gouges, and of course breaks. If we see any of those, really want to remove it from service, take an evaluation of it, and see how it can perform or how it can be made whole again. And so we'll look for gouges, stretching. Again, the tag itself should have capacity as well as who made it. And I wanted to, we've got a couple of poll questions.
Let me break in for a second, Jonathan. Yeah, I was going to launch the first poll. So we're turning this around onto you guys in the audience. So the first question, I'm going to launch it right now. It's basically, what damage do you see in the synthetic slings that you use? So I just launched the poll there. And yeah, Mark, any that apply. Jonathan can't see what's on your screen right now, but I can kind of relay over the air here once we get some votes coming in. It looks like early on it's a lot of snags and abrasion are the leading two. We'll keep it open for about 5 more seconds here so everybody can get their answers in. Not too many burns, weld splatter, hot loads, and then the UV degradation is actually moving up. I'm going to close the poll here. We can check the results. So it looks like we ended up with a lot of you guys are seeing abrasion out there. About 51, about half of you are seeing snags or missing tags. The burns and the UV degradation are bringing up the rear, though, so interesting stuff there.
Yeah, and this can really, especially for synthetic slings, this can really be sort of a deceiving point about UV and sunlight damage. You know, we've seen slings that have been bleached white, and you think it's a white sling, when in fact it was brown to begin with. And so these are kind of, if you look at some of the manufacturing dates, you can see 10, 12 years of use, and over time these things can really start to add up and take away from the capacity. I think, do we have one more for the chain slings as well?
Sorry about that, Jonathan. Yeah, we do. Same idea. What damage are we going to see in the chain slings that you guys are using now? So let me launch that one and see what kind of results that can produce. So the poll is open right now. The options are unauthorized welding, link elongation, metal loss, bent end fittings, and distorted couplers. So keep it open just for about 5 more seconds here. Again, interesting information. Far and away, so far, the bent end fittings is leading. Looks like about 80% of you guys are seeing that. Meta loss is lacking there with 16%. So I think I'm going to close the poll right now and get those results up on the screen. And yeah, again, far and away the bent end fitting, 75% of you guys are seeing that in your chain slings. Unauthorized welding is about 30%, and that's, as we know, a big no-no. But again, interesting results. Thanks you guys for participating in that. There are going to be a few more polls as we go through here. So I'll get the screen back over to you, Jonathan.
Great, thank you. Yeah, thanks everyone for taking our polls and just providing a means to discuss. It really, end fitting damage, I think it occurs a lot of times because we choke chains around all types of things. I mean, I-beams and bundles of loads, and really that's the piece that gets kind of wrapped and bent around those things, and you can see a lot of damage. We're going to take a look now at a couple examples, and I just want to talk just kind of briefly. And if you look at our first example, we'll talk about synthetics first, then chain. If you look at the damage here, I mean, we can see, you can almost kind of see this really even section of abrasion, maybe some cutting in here, and it's possible that the sling itself was possibly wrapped around an I-beam like this, and really those points of contact are going to be where we see a lot of damage. So, and some people even say, well, it's just this is just the surface strands or the surface pieces of the nylon itself, and the real strength is underneath. And gosh, this it isn't like a sheath, so to speak. The web sling has webbing all throughout it, and every fiber produces or provides some form of capacity. And so taking some of these fibers away really reduces that capacity. We also kind of notice a snag up here. If anybody else can identify anything, there's actually one more, kind of hard to see, but if you take a look down here, you can kind of see there's a snag at the bottom there, and really it provides a visual indicator that, hey, something's not right about the body of this web sling, and we can start to see a little bit of capacity being removed from that sling itself. And so we just want to make sure we're identifying these things as we see them. Let's move on to the next sample here. Possibly even the same body, but now we've kind of attached an end fitting to it, and the end fittings do count. We talked about the end fittings as sort of a link in the chain of capacity, and if we see damage there, we need to consider what other damage is present, and also consider how much damage has taken place and possibly remove it from service. But if we look at this end fitting here, we can see kind of a bowl shape on the top triangle section of this triangular master link. And I mean, man, there are design factors for slings themselves and hardware that you can attach to them, and if we see a bent fitting or a bent end fitting, man, we've jumped right into that design factor and take it up to its yielding limit, not even its working load limit, but its yielding limit, and we're starting to change the structure of the end fitting as it was originally made. Possibly also some maybe chemical or oil damage down here. A way you can tell if something's been chemically introduced to a web sling is, sometimes it'll burn and start to abrade, and when you kind of bend it around a piece, you'll start to hear little crackling taking place, and those are the actual fibers that are breaking in that web sling. So excellent excellent examples here. Let's move on to some chain examples, and immediately, if you're kind of looking right at the center of this chain sling, we kind of see maybe a crack right here, and these are just some ways to identify damage. But man, this chain link really looks damaged in some way, like it shouldn't bend, or maybe if it does, it can't bend anymore. Maybe it's been elongated further. Maybe it's possibly low carbon type fitting, which we don't typically use in rigging, and so it's a way to identify, and that's the last thing you want to see when you throw that choker around the load there. Another thing too is if you kind of notice the elongation here, typical chain links, just looking at them, tend to have a strong oval presence, and here we can kind of see we're almost pinching the middle as the chain is elongated, and it starts to suck in. It's actually one of the visual indicators of chain slings being elongated past their capacity, and so we've taken this sling into, or over capacity itself. One last place to check is the end fitting, and we can see the hook here. Possibly some nicks in the hook, maybe some metal loss. Just things to look for. Also, what happens if you put a web sling into this hook? What is that going to do to that web sling itself? So if we drape or rig a sling or other piece of hardware into that hook, what is it going to do? And will it snag on that web, or this web sling will snag on that metal loss piece? Maybe it's a sharp piece or a sharp end. And what kind of damage is that going to do? So let's take a look next at the maybe the upper works of this chain sling, and we can see I've highlighted the tag itself, and notice that there are maybe you possibly can't read it, but there are places for information to go. However, there's no information present about things like the reach itself, feet and inches, and just missing information here. So, even if the tag is present, if it's not really properly filled out or filled out at all, it's as if the tag were never there. I mean, how do we know how long the chain is supposed to be if we never know its original length and measure that against that original length? One last piece here is the master link is drastically bent. You can see a couple concavities and just throughout that entire body, and this happens commonly if we're rigging from a top-down view. We're rigging from an I-beam, say a column, and we kind of take our maybe a choker sling or choker hitch around here, and we attach a chain sling to it. Maybe the master link comes off this way, and now we've all of a sudden changed directions potentially from pulling this way to now we're pulling maybe south here, and really bending that body around the master link or the column itself. That can really damage the master link and reduce the capacity for that entire chain assembly. So we've kind of looked at some samples here, and we're going to move on, but just some examples of general use and wear for web slings as well as chain, and looking at removal criteria for those things. The next topic I want to talk about is in the advanced rigging section. The subjects we talk about often are inclined planes, low control, a lot about center of gravity, where it is, how to find it, and how to rig to it. Snatch blocks and winch systems, come-alongs and chain falls. You know, a lot of times, not every industry or not every user has a chance to experience, you know, drifting of loads, but it's a good practice to kind of get familiar with it and see what else is out there. Jack and rolling rigging is sort of the horizontal rigging that we introduce in a lot of our classes. Again, companies like, well, piece of hardware like Hillman's and Stearman. There's also, I'm sure there's lots of other horizontal rigging companies that use rollers and those types of things, but really exposing guys and gals to our different pieces of hardware in the industry. We talk about designing lifting angles, compound loading, hitch systems, and load turning. You can see here in the picture we've got a 2-crane pick going on, and the trying to minimize the load to the smaller crane itself, and really getting our guys to get our students to provide a means to calculate and figure out how to do that. And so there's a couple topics there. We're going to jump right into the learning objective here, and we'll talk about how to calculate the tension in slings and rigging hardware when rigging a load using single or multiple leg assemblies. So let's look right at this. So we've got, got a poll question here in a second, but let me kind of introduce you to the load itself. We've got a 13,000-pound load. We're going to be kind of getting expensive with our rigging and crane operations here, so we're going to lift it with 2 cranes, one on lifting lug A and one on lifting lug B, and I'll reference crane A and crane B respectively. And all we know is that we've got a kind of a center of gravity logo here, and that's kind of where the center of the weight and mass is located. And some distances, just the distance between crane A's pick point and crane B's pick point to the center of gravity. And if you look at, well, intuitively, let's talk about which crane do we expect to have the most load? Just kind of looking at it and thinking about it, and we can actually launch that poll question. Joan, if you get a second to present that.
Yeah, let me get that up here. So I'm going to launch it now. Based on the load weight and the lifting point's location relative to the center of gravity, which lifting point will lift more? So your choices are A or B, or they're going to have an equal load share. So I'm in, the results are coming in, and everybody, your answers to these polls are 100% anonymous. So I mean, if you don't know, take your best educated guess. But yeah, it's just to keep the discussion going, maybe identify some knowledge gaps or what you need to work on. So don't feel bad. I'm going to leave the poll open for just a couple more seconds here, and we can get to the results. All right, so I just closed the poll. Let me get the results up on the screen. It looks like most of us think pick point B is going to have more of the load share, so crane B, that is. About 75% of us thought that. 15% or so thought A would have more, and then 10% actually thought they'd have the same share. So interesting results, and thank you guys again for participating.
Yeah, thanks so much, guys, for joining in on that poll and sticking with us. So let's talk about kind of the concepts here, and we're talking about load share, and really load share is a basic concept for our riggers to understand, because it kind of everything builds on top of that. And so if we look at, I've got another panel to show you. If we look at Journeyman Rigger Reference Card and the panel 2 on that, we know we talk about the share of load weight at A and share of load weight at B, and we're talking about these 2 pick points. It's really a similar problem here. But if we look at how to come about these answers, we look at a term called the, let me choose colors here. We talk about an inverse relationship. That's just a fancy term for whatever happens at, between the center of gravity and, say, pick point B. We're going to use the span between A and the center of gravity to figure out the loading at B. And I'll show you how that works. It's really a cool concept. It's something everybody already knows intuitively, physically, but when we put it on paper and we get guys out in the field, this is kind of a newer concept that they have to learn arithmetically. And so if we take a look at this concept, we're going to take, say, A, for instance. And at A, if we look at the inverse proportion, inverse relationship, we know that the loading is going to be some proportion of 3 divided by the entire span, which is 7 plus 3. So this is kind of the equation, and really this boils down to what we can give as a percent or a fraction or some type of percentage of the total weight if we're only using 2 pick points. In this case we are, and so we're looking at 30% of 13,000 pounds is actually going to yield for us about 3,900 pounds at being lifted by crane A. If we do the same type of relationship with B, now we're taking the distance between A and the center of gravity and applying it to B with the entire distance between A and B. And really, we're going to get 70% of this load. And you'll know you'll have thought about it correctly and done this correctly if in fact these two come out to be 100%. Can't get more, can't get less if you're lifting with only 2 points. And so we multiply that by the entire load, and we'll get the percentage in load form at B, which in this case is 9,100 pounds. And so we start to think about, if take the entire load out of it, if this was a person sitting here, on a table at this center of gravity point, and, it was closer to, we'll say Bob on this side, and he was lifting up, and it was further away from Sally on this side. Well, which side would you rather be on if you wanted to lift the least amount of weight? And side A would be my answer. And certainly, as the gentleman slides from left to right, he'll start to increase or decrease his share of load across that distance. Excellent. Let's move on. So we've kind of got an idea of load share itself, and we've talked about A and B. We're going to get a little bit less expensive. We're going to hire just one crane now for our lift and use 2 slings, and we're going to rig over the center of gravity. Our hook is going to come up to this point here, and now that we've included an angle, and the angle I'm talking about here is this angle right here at A, specifically talking about A. If we know that, originally we're lifting 3,900 pounds, the poll question here is, will the increased loading also increase the tension or the load share, or let's call it tension, sling tension in sling A? So will this number, even though we're lifting that much, if we're lifting vertically, will we get that much less than or more than 3,900 pounds because of this induced angle, because we're lifting and rigging to the hook itself? Jonah, let's go ahead and launch that question and kind of see where we land.
All right. So I just opened it up, and just to repeat it, it's how will the load in sling A change when we lift at an angle to the horizon rather than lifting vertically? So again, the options: increased load, decreased load, or the load is the same as the load share. And yeah, it looks like this one is close to a landslide. We got 94% of the, or now 95% of the respondents saying it'll increase the load. We'll keep it open for just a few more seconds here. Alrighty, guys, get your answers in. I'm going to close it up. and then share the results. Looks like, yeah, 9 out of 10 people said it'll increase the load, and then it's split a little bit. So a couple said it would decrease the load, and then a couple said it would stay the same. So thanks again for the results, and give it back to you, Jonathan.
Great, thank you. Yeah, thanks for your respondents, guys, and we'll talk about how it actually affects that sling load, or the load inside the tension itself. So if we kind of induce the 12-foot headroom between the pick points and the hook, we still have our distances 7 and 3 between the center of gravity and the pick points itself. We wonder what the sling angle is, and a quick way to do that is just the Pythagorean theorem, and you know, I think it comes out to 13.8 feet, but you get really expensive if you go right there to 13.8 from a manufacturer's point of view, but or usually we typically round up to 14 if we need it. So I've kind of done that math for you, but if we look at the tension factor and what happens when we induce that angle, the tension factor is nothing more than the sling length, which you got at 14, and the height between the connection point to the hook and the elevation of this this lifting point here at A, which we found to be 12, right? And so if we look at, it's just we're talking about a factor here, so we're not actually going to find the load weight just yet. But if we look at the factor, we get a factor of 1.166. And really what we're talking about is we're increasing the load by 116.6%. That's really what we're talking about here, is when we induce this angle in the load as we start to rig up to the hook, we're increasing that load share in the sling tension to or by 116%. And so if we take a look at the tension in A, we know that originally we had 3,900 pounds, and if we multiply by that tension factor, we can arrive at what we think what we expect the sling tension to be when we start to lift this load. And really, this is the number, this is the loading that we should size our rigging to. And so if we had, if we had a 2-ton sling, we would have been okay, with this 3,900 pound lifting vertically. However, a 2-ton sling would be undersized in this case if we went to 4550, because we're over by 550 pounds. And understanding that, inducing that angle there to the horizon is going to increase our angle, or increase our sling tension. And so sizing our rigging accordingly is very vital. Great, I'm glad everybody was able to follow along. If you get a chance and want to do the same type of calculation, figure out the distance between the hook and B, and go from there, and you should get around 9,380 pounds. Let me know if you don't. Great, let's move on. So one of the next steps is looking at critical lift planning. We've got a course, and a lot of the topics in this course talk about load affirmation. It's a lot of checklists, and we talk about worksite approval, verification of the crane, the load travel path and placement of personnel, confirming that the rigging is inspected and rigged properly, the pre-lift checklist. All these things are kind of in the pool of responsibilities for the lift director. And so we talk about all these things and how to kind of go about the planning steps of what a lift director should do. Moving into the learning objective itself, we're looking at using a scorecard to determine the requirement of or to develop a critical lift plan. And I know in the States we don't really have a set definition of critical lift. It's really independent of the activity, but really dependent on what the company decides is valuable or risky or what have you. And so we recommend developing a scorecard internally to really determine if critical lift planning is needed. A little bit more scrutiny on the lift, There are times where we have production lifts, and you can do those things 100, 1,000 times, and they're really not gonna change. There might be standard lifts where you use your scorecard, and it comes out that really this is one crane out in the yard somewhere, not really a hazard to anybody. And then in some cases we have critical lifts, and these provide our scorecards provide a means to kind of jump into that planning and really evaluate how to determine a critical lift from a standard based on corporate priorities. So if we take a look at the critical lift scorecard, this is kind of how we organize it. We have tons of different subjects here. We've broken down the lift itself into, this is what the company prioritizes, and we can talk about man basket lifting being automatical, critical lift, or at least one of the criteria. If we use multiple crane lifts, we've assigned numbers to them, and we'll talk about what that means. We can also assign load values, and this is just one way that a company says that the replacement cost is more than we can bear. We want to provide a little bit more scrutiny for the lift that's going to occur. And moving on down, maybe even the environment that the crane is being placed in, maybe electrical prohibited zone or pressurized materials inside the load itself, or a turning type lift where upending, inverting, those types of things, and those become very complicated and should be, at least for this company, they consider that to be a valuable or a lift that requires a little bit more scrutiny potentially. And so let's, I think we got one more poll question here, Jonah, is that right?
We do. Let me launch that right now concerning the critical lift scorecard. So Jonathan just ran through some options that was on the example that we had there, but turning it back on you guys, what priorities does your company value during its load handling activities? And obviously there are more that Jonathan ran through than what are listed here. We're kind of limited. We only give you 5 choices, but if you guys want to participate in this one, we'll leave it open for about 10 more seconds here. Pretty overwhelming that the safety of the personnel is leading, and I mean obviously that's kind of a gimme. Everyone should that should be important for everybody. I'm going to close the poll here. Looks like we got a good amount of people participating. So yeah, as I mentioned, personnel safety overwhelmingly 92%, and it really should be 100% for. I mean, it's possible somebody missed that one, but no worries there. The cost of the load, that's over 50%. Damage to equipment or buildings or land around there, just over 70%. So great results again. And really, there's no wrong answer here. There are certain situations where it's going to be different, but yeah. Thank you guys again. Go ahead, Jonathan.
Yeah, thanks. And I'll identify just how we use this scorecard. Again, there's no right answer. This is really what the company itself values, and if or can place a risk profile on. Talk about replacement of the load here, loss of load, what happens to the plant or operation going forward. And so we've assigned different number values to these criteria, and some are more, some are less. And the way we kind of identify this is, or we evaluate this, is to take the values that are applicable and say we've got 3 here, we've got 0, 0, 0, and so on, and we can start to sum these up at the bottom, add them up, and we can start to see if our criteria warrants a critical lift plan to be developed. And so, this company has just chosen arbitrarily or maybe scientifically that 5 or more based on this criteria scorecard is the value that it's kind of their cutoff. And so anything above 5 and requires a CLP. Anything below, we call it, maybe they call it standard, and they kind of go on with business as just their regular standard lift procedures. And so this is just an arbitrary number. They've possibly chosen it just to, based on past experience or kind of looking at the rest of the criteria itself and kind of wargaming what that looks like. We can start to determine if a critical lift plan is needed. So you get a chance to do this yourself. We'll kind of go through an example here and look at the lift parameters just for a specific lift. We're talking about one crane here, and you may have the sheet in front of you, you may not. I've got one printed out in front of me. Just kind of going through, and we can determine and develop our scorecard as needed. So kind of looking at the lift planning parameters, it's going to be a single crane lift, and so we're going to get zeros for these. Load value is 89,000 pounds, so it gives us kind of a 1 here, and we can limit our answers to these ones as well. Let's see, no electrical hazards exist. Load's not pressurized. It's not going to be turned upside down or inverted or uprighted. We do see replacement loss of load results in 3-day plant shutdown. And so here, if we see, if it's more than 2 days, we're going to get a loss. We want to activate this criteria by including it in our sum total. The other piece of information here is load replacement is 5 weeks. We've got anything as more than 3 weeks as our criteria. Oh, correction. We move here and there. Not using math baskets at all. So if we kind of tally these up, we see we get 8 as our answer. And if we're being honest and we kind of look at, oh, pardon me. If we're being honest, we kind of look at our evaluation criteria. We know 5 is less than 8, and so this kind of triggers a critical lift plan to be developed. We want a little bit more scrutiny for this plan, and we're going to move forward with that. So just a tool to use, maybe internally in your own organizations and crane and rigging operations. Great. Let's move on with the next. It's kind of a quick topic there, but hope everybody's engaged and interested. We're going to talk about mobile crane inspections, and just sort of the training subjects here are inspection requirements, and those are based off of some of the things we find in OSHA and ASME, and as well as other federal regulations. How to do it safely, how to do these inspections safely, what components we use or we inspect. We'll talk about kind of those different components, and then other additional safety items. Sort of the how-to when we actually kind of go in and break down a crane and look at its parts and pieces and make sure that it's still operational. So the learning objective here is able to identify and locate and inspect the crane's mechanical system. And we'll talk really specifically about one piece of that mechanical system. In general, we talk about inspections. We really want to organize our thoughts around a simple acronym, and we use MESH as our acronym. You may use another one, but MESH stands for mechanical. It could be anything from the engine itself that drives the drums, as well as wire rope. We tend to think of wire rope as a machine, and so it's got moving parts, and if one of those moving parts is not moving, then we don't have a machine anymore. And so we really want to take a look at that wire rope, as well as the engine and anything else inside the crane that deems it to be in that mechanical area. We looked at the electrical section. These are the strain gauges. These are the LMIs, the load moment indicators, inside the cab there, as well as any other indicators that we get electronically. make sure those are functional, operational. Next one is structural, everything from, you see the jib section here as well as the boom section. Any piece that is load bearing or load carrying, that includes the outriggers and the floats themselves, is, make sure they're not cracked and damaged or unable to carry their loads. And then the last piece is hydraulic, and typically mostly all of our cranes are hydraulic or have some type of hydraulic system in them. This is the boom hydraulic cylinder here, and then also the jacks and outriggers themselves have cylinders as well. Just making sure they're fully functional. The lines are not leaking, no cracks or excessive wear. So just a way to organize our thoughts. We're going to take a look more specifically at SHEAVE inspection. This is kind of in the mechanical realm. And sheaves are found all over. There's rooster sheaves, there's upper boom sheaves, sheaves for hoist rope. And this is specifically for the hook or block sheaves. And really what occurs inside here and why it's so important, we'll take a look at how to inspect them properly. So some of the tools that we use for this are the SHEAVE gauges, and the gauges themselves kind of range all different sizes. They come in different materials as well. There's some aluminum or plastic, a little bit lighter weight, and we'll see another property there that's also useful. Inspecting specifically, we want to make sure that if we're inspecting sheaves, we want to ensure that they have a correct shape, and the shape really is important because it holds the wire rope itself. If it's too wide, typically wire rope wants to be round. It's where it finds its most strength. And if we induce a shape on it, such as maybe a wider bowl through the sheave, it's gonna end up, wire rope itself is gonna end up flat as it passes over, or flatter as it passes over through that sheave. Again, similarly, if we pass through a sheave that's worn down but not necessarily out, we find that the sheave itself becomes sort of pinched in this sort of egg shape, and really does not allow the strands and the wires to move properly as they should. And so we want to make sure that when we're inspecting our sheaves, we've got good contact throughout. There's a instance here where we look at the amount of contact, and about 150% is what we're looking for. Anything more or anything less really puts a question in our mind about what the wear is in these sheaves themselves. So we talked about sheave inspection with just in general, but we want to take a look at plastic sheave gauges. This plastic sheave gauge here. And if we look at, some of these sheaves are in places where, very dark lighting, very hard to see potentially, and it's hard to tell where this interface is between the sheave sides and the sheave gauge. But it's easily remedied, at least with plastic sheave gauges, if we add some type of light source behind the sheave gauge and kind of look at it from the other side, and we can clearly see, there are gaps between the sheave itself and the gauge. And right here is where we start to question, maybe we're inducing that flattening of our wire rope as the sheave or the wire rope passes over the sheave itself. So just kind of a nifty trick. You can also do this with metal sheave gauges and just kind of look at the light that passes around the sheave gauge itself. So just one of the tricks of the trade. My inspection toolkit, we've got magnifying glasses with lights on them, and really useful technique here. Moving into the next training subject, that was kind of quick and easy, but let's move into mobile crane operations. And some of the training subjects we talk about here are they're really very similar to what we see in rigging itself. And we talk about center of gravity. We talk about calculating capacities, boom angle, pick and carry practices, as well as reeving itself and how capacity is affected by that, gross and net loads, as well as all the applicable standards. Moving into the learning objective here, we're going to take a look at being able to accurately determine the crane capacity for load radius, boom length, and boom angle given a load. So let's jump right into to our subject here. Hey, we've got the same load as before. We're gonna add a crane to it. So we've got 13,000 pounds load weight, and we're gonna be lifting it with a Grove 890E rough terrain crane. And if you're not familiar with mobile cranes, it's no don't be afraid or shy away. I'll kind of introduce you here. The main cab area where the crane operator is housed sits here and has all his controls and can operate everything from that position. We've got the outriggers that connect our crane to the ground and provide stable footing. There's one more right back there, and one more right there. The boom itself, we talked about kind of the structural integrity of the boom. We've got a main block here and an auxiliary block there, as well as the counterweight in the back. So you know, just tucked up underneath here's the jib, provides a little bit more reach, and we'll talk more in depth about how to develop the capacity for this this crane and how to ensure that we can lift the loads that we're asking it to lift. So we've got a little scenario here. We'll talk about the scenario and then ask a poll question quickly. We want to look at our approved crane area. Maybe it's the pad size is the approval aspect of this, or maybe the ground has a ground bearing pressure allowance, and so we're able to set up here. But just in our scenario, we can look at where we want to begin our lift and where we want to finish it. Maybe we're moving across the yard and this is its final position that we want to be in. One of the first things we need to know is the radius, and we measure the radius from the center of rotation. I'll kind of mark that here with an orange dot. We measure from the center of rotation to the center of gravity of the load, which is so important to find the center of gravity first of the load and then kind of work backwards from there, because eventually, ultimately the hook is going, or the load is going to find itself under the hook once the load is lifted. And so if we look at some of these numbers here, that's 50 feet, if you can't see it on your screen, is the start radius, and the finish radius is 65 feet. And I want to ask a quick poll question, just in terms of what you think intuitively. Should we have more capacity or less capacity based on the radiuses we've identified here? And Jonah can take that away.
Okay, let me launch it here, guys. All right, the poll question's up now, and just to repeat it, it's which radius do you expect the crane to have the lowest capacity? And then your options are 50 feet, 65 feet, or both radii will have the same capacity. And this one early on is looking like a landslide. Looks like we got about 90% of our attendees are thinking it's 65 feet. Nobody thinks that they'll be the same, which is interesting, and 10% at 50 feet. So I'm going to close that one. Looks like our results are fairly unanimous on that. So 9 out of 10 people think it's 65 feet. We have the one that maybe the calculations are a bit off, but it's 50. But interestingly enough, nobody thinks that they'll have the same capacity. So thank you guys again. I think there is just one more poll coming up, so it's great to have this feedback.
Yeah, thanks again, guys and guys and gals. And this, without looking at the load chart, it may be kind of a weird load chart where maybe one is higher than the other, or we have the same capacity. But in general, if we look at this this concept, we have a person here who holds a bucket of water. It's a really long arm a bucket of water out over or out across from their body, you just think kind of to yourself and in your mind about, am I going to be able to lift this bucket of water out extended, or will I be able to lift a little bit more water in my bucket if it were closer to my body? And really we're going to have less capacity in general the further away from our center of rotation that we get, and that's kind of the concept there. Talking about the load itself, we talked about the entire load, but there's some other additions, deductions, and things that apply to the crane and how we would need to account for those things and how they go into the capacity of the crane itself. So we talked about the rigging. There's actually, rigging weights made of steel or heavy materials, and so we need to account for that weight. There's rope reeving itself, so anything between, some crane load charts say, between the boom tip itself and the load, just count all those parts of reeving and multiply by the unit weight, and you get the loading there. The main block has a weight as well as the auxiliary block, even if you're not using it. And so all these things kind of count into our total capacity or total gross load to be lifted. And that's the number we're actually going to be using to find our capacity. So moving into the load chart, I'll just, a quick orientation of the load chart. We've got really some qualifiers to jump into this load chart itself. We want to make sure that our outriggers are 100% fully spread. We're using 22,000 pounds counterweight. This load chart is only good between 37 and 141 feet, and it's also good for 360 degrees, so any quadrant of operation. The next piece is the radius itself. We calculated that before, and we could find that in general you'll see increments of 5 as we go, and that's just the radius between the center of rotation, like we talked about, and the center of gravity, and that's how we kind of jump into this whole chart. Next piece here is the boom length, and this is really for the operator to assist him or her in determining how high they need to be, or what boom position they need to be at to lift the load. This also could have something to do with how high can I place the load. So if I run out of headroom, we'll call it headroom between the ground and the boom tip, it can really make an effect if we have to lift the load to, say, 120 feet, but for instance we only have 115, that may cause a problem. We may need to reevaluate our lift. And so the last piece here is the capacity piece, and that's what's in the body of this entire document. We've got capacities on top and boom angles on bottom, and so these are just helpful identifiers to help the operator determine where he is on his load chart. So moving into our example here, we're going to answer this question. We're going to figure out, or given the furthest radius of 65 feet, we're going to figure out what is the highest capacity we can have to lift this load. And we looked at, intuitively we all think that 65 feet is going to produce a lower capacity for the crane, and it's absolutely right. We're going to find out. So it's a good place to start, and we'll check the 50-foot radius afterwards just to confirm that we have capacity in both radii. And so looking at kind of jumping into our capacity chart here, we look at the radius first. We read over, and we can see we've got 13,850, 52, or 15,200. We know that we have a gross load weight of 15,900 pounds, and once we come to 16,150, we have a choice to make, and really we're asking for the highest capacity we can achieve, and the highest here in this case is 16,700 pounds. And so that gives us a little bit of a margin, a little bit of an envelope to provide some stability and safety. And so it's interesting, we actually get more capacity at a higher boom length than the next one over, 102 feet. So just an interesting thing about Grove cranes, or this Grove crane specifically. So we can identify this as the highest capacity for this radius. And then we're going to just check the 50-foot radius and just kind of read over at that same boom length. And we'll see that it's 22,050 pounds, which is much greater than our 15,900 pound gross load. And just as a helpful hint to the operator, we can say that, hey, you should be about 115 feet of boom length. So if you've never been introduced to crane load charts, you just have, and hope it was a easy, good experience for you. There are much more deductions. The small fine print of crane load charts can be kind of daunting sometimes, but nothing to shy away from for sure. Let's look at our last topic here. We're going to be introducing a rigging engineering program and just kind of an overview of the courses that we're going to be offering. Everything from an introduction, cranes and derricks, rigging equipment and applications, alternative LHE or load handling equipment, and then lift planning itself. So this could be a really good course for the senior supervisors, lifting engineers, any of those types of roles and responsibilities in your organization could really benefit from this course. I recommend taking a look at riggingengineering.com. Take a look at the instructor list. We've got some great names up there for you, so take a look at that. One of the learning objectives inside this is just kind of a piece that we're going to be talking about is determining load stability, kind of a nebulous term there, given a known CG location and sling angles. So let's jump right in. Taking a look at this lift, we're going to look at what stability versus instability means. And gosh, we got this huge load here. We've got a little bit of counterweight in the back. We've got a big excavator arm in the front. Manufacturer provided lift lugs on all four corners there. But even though the manufacturer provides these lift lugs, how do we know how to rig it? These could be tie-down points as well as lifting lugs. And how do we know that our rigging configuration is going to provide a stable platform for this excavator to be handled? And we'll take a look at this example a little bit later after we discuss what instability versus instability is. I like to start off with instability first. We kind of know what that inherently is. This is Nick Walenda. He's a gentleman just I think this time last year went across the Grand Canyon, and he inherently knows something about instability and how to remain stable. But if we kind of look at his profile, center of gravity is kind of centered there, and he knows inherently that he has an axis or a point that he's moving about, kind of a hinge point right there. And inherently we know that I think the pole's open, kind of a tongue-in-cheek pole there, but go ahead and take that, and we'll see the responses in a second. But if you look at what is inherently wrong with this, is that we know just looking at it, if some of you said, no, heck no, I'd rather not do this, we know that inherently he wants, or his body wants to fall over that hinge point. And so we can understand this idea of instability really easily. This is a monkey, and what a monkey knows is that when he hangs underneath a limb by his hand, his center of gravity is below that hinge point that we talked about before. And no matter what he does, whether he swings out either way or up and down or what have you, he'll always come to rest so long as his little paw there sticks to that limb. He'll always come back to rest back underneath his hinge point. And so inherently he knows he's in a stable position unless he lets go. And that's the only thing that can really take him out of that unstable or that stable position. So now we kind of have an idea of stability and instability. If we apply this to a rigging problem, we can look at the lift points here in this load, and just kind of lifting with one crane at 2 points. Here they're both kind of centered transversely across this load itself and above the center of gravity. And so if we look at where that hinge point lies, we have what appears to be sort of we call it a monkey situation. And this is where we can start to identify load stability, and we inherently know that this load wants to come back to center if in case it does get unstable for a brief moment of time. Maybe we're lifting or hoisting up, and maybe the hook isn't exactly centered over the load itself, and maybe the load swings out just maybe a couple feet, but we know that inherently this center of gravity of this load wants to fall underneath that hook. So we've got a stable condition here. Let's take a look at another example where we've changed our lift points to below the center of gravity, but our hook and our sling attach above. And so the first thing we need to do is figure out, gosh, where's the center of gravity, and then where's our hinge point? And our hinge point is going to be the same location. This is kind of where this load wants to move out or move into in terms of center or stability. And what we can say here, we have 2 cranes even, and this configuration is even on the other side, lifting the other position there. When those 2 cranes lift, even though we're seemingly capturing the center of gravity, we want to make sure that it doesn't come out of its sort of triangle here. And there's actually a way to look at that and measure it. And if we look at the sling angle made by the sling itself and the lifting point, we kind of see this stability triangle emerging, and it's capturing the center of gravity. And the next thing we want to know is, what is the angle from that same lift point or lifting lug to the center of gravity? And if, in this case, if angle B is greater than angle A, we know I have a stable position, at least to the point where if we check the dynamics, this center of gravity won't move outside, possibly by overturning or sort of dumping the load, so to speak. And so care is going to have to be taken for what we're comfortable with. And in a lot of cases we recommend placing the center of gravity, if you can, in the bottom third of that stability triangle. And it doesn't prevent overturning, but it definitely provides a means to fight against it. And so we can check these angles and just ensure that we have a stable position. One of the next pieces here is that you often, every once in a while, you'll see a crane accident, and without even knowing it, the rigging method will have been produced in this manner. The hinge point in this case is below the center of gravity, and we can see that we have a man on a tightrope type condition where our center of gravity is at the whim of gravity itself. And we can see that this same situation or the same rigging configuration were placed on the other side, and we're lifting with 2 cranes, that we have, we can still check our sling angles. And even though it's lifted with 2 cranes, we say, well, we've got, looking at it from the top, we've got a whole load here, and center of gravity is right in the center, and I've got two cranes lifting on either side of it with 2 slings, and we're hoisting. We've got it captured, right? And the problem is that when we look at our sling angles, not only is this an extreme sling angle just for its method altogether, but the hinge point is below the center of gravity, as well as this angle here is much less than the angle of that same center of gravity point to the lifting lug here. And so we see that we're inherently in an unstable position, and like I said before, we've got the tightrope walker situation. And so we can start to visualize, what this looks like and how we can engineer or reconfigure our methods of rigging to overcome this problem. Let's take a look at our first example we saw originally, and we kind of drew a little center of gravity logo here. Looking at it from the side view here, we can notice that we are in a monkey. It's kind of a weird term, funny term there, but we're in a monkey situation here, and we can see that the hinge is above the center of gravity. But how do we ensure that the sling angle is much greater than our angle to the center of gravity itself? Well, if we take a look at the angle made by the sling, it's B, and we can take a look also at that same angle to the center of gravity, or that same lift point, and see that B in this case is much greater than A. And when we said that before, we knew that we were in a stable pendulum type position. And so if we take that same criteria over to the other profile view, sort of the front profile view of the excavator, now we've introduced sort of a rigging question or rigging problem, and spreader beams and lifting beams are exceptionally helpful to get sling legs out from around loads, as well as spreading the load to the actual pick points that the manufacturer provided. But how do we translate this stability versus instability question to this view? And what we can do is we have the same similar monkey situation this way, didn't change. We can look at the sling angle on top, and what I can say is that the sling legs themselves translate whatever happens above the spreader beam to what should happen or what will happen down below. And we can actually translate that angle down over the center of gravity, kind of overlay it there, and then see what the actual angle is between the lifting lug and the center of gravity. And in both cases, in both views, we can see that we have a stable position. And so this excavator, without any acceleration due to the operator or anything like that, we should have a stable position throughout the lift. You can obviously imagine where this can go wrong. In this case, a company was lifting a much smaller excavator than this one, used the same rigging configuration here, did it just fine, had to move another one, had to move a much larger excavator, and just kind of based on where these sling angles come out and the center of gravity, much higher up on this excavator than the sling angles could afford. If we put it there, we can see that as the upper slings become lower to the horizon and really get underneath that center of gravity, we can see that we have that hinge point there, and we're really in this tightrope situation. And so you can see where this can go wrong. It's really helpful to really identify where the center of gravity is and how your rigging configuration can capture it with the stability triangle. I know I went a little bit over time. I really appreciate everybody staying on who could and going along with us and through all of these different little modules and snippets of information and knowledge. And if anybody needs to contact me or would like to talk more about training itself, you can reach me at jonathan@iti.com or reach out to Jonah at iti.com, and happy to provide any feedback or any help we can. With that, Jonah, if you want to close this out, that'd be great. If we have any questions, that'd be super.
Yeah, and like you said, we want to thank you everybody for joining us. We want to be respectful of your time. I did want to get to one question. Paul asked, and this is specific to your experiences, Jonathan, but he asked this during, I think it was either the mobile crane inspection or the rigging gear inspection portion. Just from an incident standpoint, you being on accident investigations, things like that, what are some, without getting into specifics obviously, but with the company and what happened, but what common failures or assumptions have you seen that have led to failures or incidents?
Yeah, so we're really talking about really some of the more common accidents we see are rigging incidents, and specifically we're talking about methods. A lot of time we'll see field or on-the-job type configurations and really hardware and equipment that is not designed or created by a manufacturer, and even even a user can repair hardware so long as and SLING so long as they retag it and they notify everyone that listen, we've taken ownership, we've modified this equipment, and we're now tagging it as our own. All too often we'll see maybe not the methods, a better term might be the configurations of hardware that's field created and field used, and you may go through your inventory and see maybe a manufacturer or a fabricator at a facility could have his own rigging locker and using equipment that is just right for the job. He knows he's used it for a lot of years, and it works for the piece of equipment that he has. He doesn't want to lose that piece of equipment because he had to go find other slings and hardware to make the same lift. But really, these they don't have maybe certain design factors or design criteria built into them. And maybe most cases, if you're looking at slings, for instance, chain has a 4-to-1 design factor. Synthetic has a 5-to-1. Same for wire rope. And these design factors are built into the system itself and created by the manufacturer to ensure that things like dynamic loading and general wear of the sling does not compromise the capacity of the sling itself. And so we can see that in my experience, the configurations themselves, modified equipment, are kind of the leading causes that we've seen in the past. That was a great question.
Okay, well, and again, we did go a little bit over. I said 60-ish at the beginning, but thank you to Jonathan for sharing your experience with us. And just so everybody knows, that was a very high-level overview of each of the 6 subjects we touched on. All of the courses that correspond with the workshops that we did are days long, and we just went through them in an hour. So thank you guys. And again, thank you, Jonathan, for your time. We do these every month. I'm sure most of you guys know this. We have a pretty good holiday schedule lined up. So then the October Showcase webinar should be posted soon. But I think with that, we're going to sign off. And again, thank you guys for participating in the polls. It's all about starting a discussion and finding out where we can improve and make the industry as a whole better. So thanks to everyone for joining us today, and we'll see you again next time.
Great, thank you.